Hi, I'm Kathy Levinger. In this lesson, we're going to look at some applications of those exponential functions. The exponential model shown below represents the amount of bacteria in a colony as a function of time t. And here's the model. It reads P of t equals 2,000 times 1.05198 to the t power, where t is time in hours, and P of t is the number of bacteria. Well, we want to do two things with this. First of all, we want to use the model to determine how large the colony will be in 2 hours. In other words, we want to find P of 2. On a calculator, we're going to find 2,000 times 1.05198 to the second power. So let's grab our calculator and enter 2,000 times 1.05198 to the second power, or squared, and push enter, and I get the result 2213.32. and let me show you how I entered that on my calculator. You can see 2,000 parentheses 1.05198 squared, and the answer is 2213, and so forth. Well, let's write that number down. 2213.3 bacteria. Well, we want to answer another question using this same model, and here's the question we want to answer. We want to use the model, as shown above, to determine how large the colony will grow in 1 day. Well, 1 day is 24 hours, so we're going to find P of 24, which is 2,000 times 1.05198 to the 24th power. We'll definitely want a calculator to help with this also. So let's enter on our calculator 2,000 times 1.05198 to the 24th power, and we get 6,748.536 and so forth, and we'll write that number down. 6,748.5 bacteria. Let's look at another example. A sample of a radioactive substance initially contains 1.2 grams. After 1 year, there are 1.18 grams, and after 2 years, there are 1.16 grams. The first thing we want to do is use the information in the problem to find B. Well, what we can do is organize the information into a table. And in our table, we'll have time, and we'll have the amount. At time 0, or initially, there are 1.2 grams. After 1 year, there are 1.18 grams. I need to extend my table just a little bit. After 2 years, there are 1.16 grams. Now, looking at the information in the table, to find B, what we're going to do is divide 1.18 by 1.2, or we could divide 1.16 by 1.18. We should get the same ratio. If we do this division on a calculator, we end up with the number. Well, let's go ahead and do that calculation on our calculator. We're going to divide 1.18 by 2, and we end up with, not by 2, sorry, by 1.2. Let me correct myself here and redo my calculation. 1.18 divided by 1.2 is 0.9833, and I'll show you how that looks on the calculator keypad. 0.983, we'll round to 3 decimal places. And that's what we'll use as a value for B. Now we want to write a model for the decay of the substance. So we'll use A for amount. A as a function of time is equal to the amount we had initially, 1.2 grams, times what we calculated for B, 0.983, to the t power. Now we want to use our model to predict the amount present after 40 years. So we're going to put 40 for t. We're actually going to find a of 40 by calculating 1.2 times 0.983 to the 40th power with our calculator. So let's go back to the calculator and enter that. We want to enter 1.2 times 0.983 to the 40th power, and I'll push the enter button and then let you see how that looks on the calculator. You can see that the answer is 0.60439, etc. And so we'll write that down. And that number of grams is the amount present after 40 years. Let's try another example involving exponential functions. Christine invested $1,000 in an account that will accrue interest at the rate of 4.96% per year, annually. Write an exponential model for the amount Christine has after t years. Well, it feels like there's a little bit less information given here, but we can set up a table that will allow us to find the amount, or the base b for our exponential function. We have time, I could call it t, and amount of money. Let me just put a $sign there. We know at the beginning of this situation, or at the start of the investment, we have $1,000. After 1 year, whoops, if that's the interest rate, the amount of money we'll have is the $1,000 plus this percent of 1,000. So to find the number that's going to fit here, we're going to take 1,000 and add 0.0496 times 1,000. And if you like, you can use a calculator to find that number. 1,000 plus 0.0496 times 1,000, which is 1,049.6. Some of you should have been able to do that without a calculator. And so we'll put that in to our table. And now to get the base b for the exponential function, what we need to do is take 1,049.6 and divide by 1,000, and what you should see is the number 1.0496 as the base b. Take a look at this number. Notice that it's 1 that could represent 100% of what we started with, plus the interest rate written as a decimal. In a situation like this, as long as the interest rate is annual, that will always occur in order to find the base b. Well, now we need to write the model, and I'm going to write it here on the right-hand side. Pick a number to represent the amount. Let's use A. The amount, or the initial amount, the vertical intercept is 1,000 times, we'll put in 1.0496 to the t power. That's kind of squeezed in there, so I'm going to write it down below. Our model is 1,000 times 1.0496 to the t. Now we want to use our model to predict how much she will have after 20 years if she leaves her money invested in this account accruing 4.96 interest per year. Put in 20 for t, and we'll use a calculator to find this number. So on our calculator, we're going to enter 1,000 times 1.0496 to the 20th, and that's $2,633.16. In this section, we've looked at applications of exponential functions. Be sure to work lots of exercises from your textbook for practice.